Today we're going to talk about the direct comparison test. Now, we've learned several tests so far. We've talked about the geometric series test, alternating series test, nth term test, integral test, the telescoping series test, and I think p-series test. So that's 6 things we've learned so far. Now, they're nice and they do help us with a lot of different series, but in some ways some of those rules are quite fragile. And let me explain what I mean. Let's look at this. The series on the right is geometric, and so we can use a very nice rule for that. If r is less than 1, absolute value of r is less than 1, then you converge. If it's greater than or equal to 1, you diverge. Okay, but the series on the right, all we did was add an n on top, and suddenly it's not geometric anymore, and it makes this a lot more difficult. Okay, similarly, if you look at this one, the series on the left is p-series, 1 over n cubed. Use an easy rule. If the power is bigger than 1, it converges. If the power is between 0 and 1 or equal to 1, it diverges. But all we did is add a 1 to that series on the right, and suddenly it's not p-series anymore, and the test doesn't apply. Very small changes make it very difficult or even impossible to use some of the rules we've learned. Okay, here's another example. The series on the left we could do by doing the integral test without too much difficulty. U substitution would work well. But on the right, just by changing the n on top to n squared, we've made it extremely difficult to integrate. So you can see how very subtle changes can ruin our ability to use some of the rules we've learned. And that's really kind of a shame because, why should we be ruined just because we have a slight change to the series? So this is part of how the direct comparison test helps us. So this is a theorem from our book. There's nothing special about that number. It's just the one in our book. And it says, let 0 be less than an be less than or equal to bn for all n. Okay, what you need to take from that is an is the smaller sequence, bn is the bigger sequence. Okay, so in other words, an is always below or equal to bn, and bn is always above or equal to an. So an's the smaller one, bn's the bigger one. So here's what the theorem says. If the bigger series converges, then the smaller series converges. And if the smaller series diverges, then the bigger series diverges. So it's important. This is another time where it's important to focus on what it does and what it does not say. So I'm going to try to use some pictures to help illustrate this. So we'll say the A is red and the B is blue. Okay, so let's first focus on the two scenarios they do talk about. Okay, remember, B is our bigger one, A is our smaller one. So if B converges, now this is just for sake of illustration, you don't need to take it literally or mathematically, but if B converges, you know it goes to a set number. It doesn't go off to infinity. Okay, so if B converges, well, if B is the bigger one, that means A has to stay below it. So there's nothing A can do but also converge, because it's kind of like B serves as a ceiling for it. B is the bigger one, so if the bigger one converges, well, the one that's smaller than it obviously has to converge, because if the bigger one goes to a finite number, then anything smaller than it is also going to be a finite number. So it's kind of like the B keeps the A from going off to infinity because the B is the bigger one and it's converging. Okay, now the other scenario they talk about would be if A diverges. So if A goes off to infinity, well, B is bigger than it. So B has no choice but to stay above it, and it must also go up to positive infinity. So this scenario goes with this, and this one goes with this. So if you think through that carefully, it should make sense. If the smaller one diverges, meaning the smaller one goes to infinity, well, clearly the bigger one is going to go to infinity also. And just in case it's kind of thrown you for a loop thinking, how do you get bigger than infinity? Just think of it more as one's going there faster. So it really has more to do with the fact that A is going to infinity and B is even bigger and faster, so it's going to infinity even faster. That may help you think about it. So those two we can use. Now, like I said, it's important to focus not only on what this does say, but what it does not say. Okay, so this says if the bigger one converges. Well, let's talk about what happens if the bigger one diverges. So if the bigger one, B, the blue one, diverges, goes off to infinity, well, we really don't know what happens to A, because A very much still could converge, or A could just go and diverge. It's free to do either one. The fact that B is bigger than it doesn't constrain it at all, because if B is going to infinity, well, A could also, or A might, converge. So this is a big question mark. In other words, if the bigger one diverges, that really doesn't help us. That doesn't constrain the smaller one to do anything one way or the other. The same is true if we say the smaller one, the A, does converge. So A converges. Well, that doesn't give us any information then about the bigger one. The bigger one certainly could diverge and go off to infinity, or it could just converge to a slightly larger number. So it's important to keep these straight in your mind, and hopefully these pictures help illustrate it for you. If the bigger one converges, that creates a ceiling, so the smaller one must also converge. If the smaller one diverges, that creates a floor that goes up to infinity, so the bigger one also diverges. Now, again, the other scenarios don't give us a conclusion one way or the other. So let's look at our first example. Actually, before I start the example, I want to just make sure this is clear. This is almost always used for things that are similar to p-series and geometric series. It's not that it's not possible to use it for other scenarios. I'm just letting you know realistically that's when it's most often used. It's used most often for things that are similar to geometric or similar to p-series. So if you look at this one, this is similar to geometric. And here's what I mean. If we just ignore the 2, we have 1 over 3 to the n, which is really just 1/3 to the n. Okay, so that's in general what you want to do when you're looking at these, is kind of ignore coefficients, ignore constants, and see what it's similar to. So this one is similar to a geometric series, and it's similar to a geometric series that converges. So 1/3 to the n. Now go back to our theorem. If we know this one converges, then to be useful, we hope that it's the bigger one. Because if the bigger one converges, we can actually figure something out. So we're hoping that 1 over 3 to the n is greater than or equal to 1 over 2 plus 3 to the n. Now I've got to put a question mark here. We're testing this. We're not claiming it's true. We're testing to see if it is true. So I want to determine if 1 over 3 to the n is greater than or equal to 1 over 2 plus 3 to the n. Because again, if that's true, then we know that they both converge. Because if the bigger one converges, then the smaller one will also converge. So to do this, we just simply need to cross multiply. I do 1 times 2 plus 3 to the n, greater than or equal to 1 times 3 to the n. And clearly, that's true. Obviously, adding 2 is going to make something bigger than if you don't add 2. And you just simplify this as far as you need to. If you need to go ahead and subtract the 3 to the n's to see it, 2 greater than or equal to 0, that's fine. If you don't even need to take that step and you can see it when it's in fraction form, that's okay too. So whatever makes it clear to you whether the inequality is true or not, you go that far. So the inequality is true. So what we've proven is that 1/3 to the n over here by the geometric series test converges, and also that it is bigger than this series right here. And since it's bigger than that series, that means this series must converge as well. Okay, let's try another one. We have 1 over 2 plus the square root of n. Now I'm going to go ahead and give you a heads up that this one's a little bit tricky. First thing we want to make sure, or we want to check, is it similar to a geometric series, or is it similar to a p-series? Well, it would be similar to a p-series, because if you ignore that 2, it would be 1 over the square root of n. And we know that 1 over the square root of n would diverge, because the power is less than 1. Okay, now if we know this one diverges, go back real quickly to our theorem. We're hoping that it's the smaller one, because if the smaller one diverges, we can conclude the other one diverges. So let's try that. Let's see and test, is 1 over the square root of n less than or equal to 1 over 2 plus the square root of n? Well, if you cross multiply, That does not work. Now listen very carefully. That does not mean that the original one converges. Our inequality not working doesn't tell us anything except that we got to try something else. Okay? So it turns out that 1 over the square root of n is not going to be a helpful thing to compare this to. Okay, now you can go with your intuition here. Your intuition is generally going to be right. It is very similar to 1 over the square root of n, so we would expect that it is going to diverge. So what I would say then is try something else. Try something else that diverges that might help you get this worked out. And in general, that means going even simpler. So what I mean here is we have 1 over the square root of n, so let's just take away the square root and see what that does. 1 over n also diverges, so we would hope it would be the smaller one, because if the smaller one diverges, then this should work. Now if we cross multiply, we get 2 plus the square root of n is less than or equal to n. So if you're not really clear on whether that's true or not, I'll go ahead and tell you it is, and this is going to work for us. But if you're not really clear on that, one thing you can do is go to the calculator and plug both of these things in. So I plugged in 2 plus the square root of x into y1 and just x into y2. So what I'm hoping is that y1 is always less than y2, because that's what's being tested in the inequality. So I just went to my table and plugged in 1, 2, 3, 4, and then 10, 100, 1,000. Okay, now if you notice, y1 is actually bigger for those first few terms. But as you go out to infinity, it's clear y1 is always smaller. I mean, at 10, y1 is just 5 something, 5 and some change, and then y2 is 10. At 100, y1 is just 12, and y2 is 100. At 1,000, y1 is just 33, and y2 is 100. Okay, this inequality does not have to be strict, and what I mean by that is if the first few terms don't work, but every term after that point does, that's okay. Because if you think about it, adding up some bigger numbers at the front end don't matter if we're doing the same thing as we go out to infinity. When we've got an infinite number of terms, what's it matter if the first 4 are a little bigger than the other 4? So this actually does work, because at least once we get past n equals 4, this will be true. And that's what we care about, is what's happening as we're going to infinity. So clearly n is going to move faster toward infinity than the square root of n, even if we add 2. So we're going to say this is true, and since this is true, that proves that they both diverge. So I just want to make this clear. What you're doing is you're finding something you can compare it to that you already know whether it converges or diverges. You set up an inequality, and if the inequality holds true, it proves the two of them do the same thing. If the inequality doesn't prove true, then you need to try something different to compare it to. Here we have another example, 1 over e to the n squared. This may not immediately look like geometric or p-series to you, I don't know, but it actually is very similar to geometric. If you simply drop the squared, it's 1 over e to the n, or you can write it like this if it's easier for you to see. Now remember, e is a number, it's 2.71, so 1 over 2.71 something is going to be less than 1, so this converges. So we suspect that the other one will converge as well. Okay, if you think back to the theorem, it's helpful when the converging one is bigger. And if you can just remember, converge bigger, diverge smaller. Converge greater than, diverge less than. So that's how we're going to set this up. Since it converges, we're going to set it greater than or equal to 1 over e to the n squared. Now I cross multiply. I get e to the n squared greater than or equal to e to the n. Well, that's got to be true. You square something, it certainly makes it bigger. So this is true. So that proves they both converge. One more example. We have the natural log of n over the square root of n. This is a p-series. This is similar to p-series, excuse me. It's not actually p-series, but it's similar to p-series. 1 over the square root of n. Okay, and we know 1 over the square root of n diverges, so let's see if this one's more helpful to us this time than it was last time. So diverges, we want to see if it's less than or equal to the other one, because if the smaller one diverges, the bigger one diverges. Okay, now we cross multiply, 1 times the square root of n, less than or equal to natural log of n times the square root of n. Okay, and this should obviously be true to you as well. Um, multiplying by the natural log is going to make something bigger than if we don't multiply by it. So this holds true, which means they both diverge. So hopefully that helps get you started. Some places you can look for practice are on page 587 in our books, around 3 through 14.